Let's see another example. For g of xy equals ln of x plus y plus 1 over x minus y, evaluate g of 0, 1, then find and sketch the domain. So g of 0, 1 means put a 0 in for the x and a 1 in for the y. That gives us ln of 2 over negative 1. In other words, negative ln of 2. So what does this tell us? It tells us that if we look at the point, oops, I've got my x and y backwards. It tells us if we look at the point 0, 1, which is a point right on the y-axis, then the dot on the actual surface, on the actual graph, will be, well, it's negative, so it's going to be below the xy plane. So it's on that back wall because the x-coordinate is 0. How far below the xy plane is it? Well, it's ln of 2 units below. So I didn't put the minus in because I'm just talking about the distance there. But the z-coordinate then is minus ln of 2. Again, we don't know what the entire surface looks like. We only know where one dot is. We'll talk later about how can you tell what the surface looks like. But in the meantime, let's find and sketch the domain. So there's two things going on in this problem. First of all, the input to the log function has to be greater than 0. It can't be equal to 0, so I'm not going to put greater than or equal to 0. It's got to be actually positive. Remember, you can't take the ln of 0. But we have a second issue here, and that is we've got a denominator, and the denominator cannot be 0. So how can we sketch this? Well, first of all, since we're sketching in the xy plane, let's solve both of these statements for y, because that's how we're used to thinking of things in the xy plane. So if I subtract x and subtract 1 from both sides of the inequality, I have that y has to be greater than negative x minus 1. And then for the second statement, x minus y can't be equal to 0. That's equivalent to saying that x can't be equal to y. And we're just working in the xy plane here. So what does the graph of y greater than negative x minus 1 look like? You might need to review graphing inequalities, but I'll remind you, basically the way this works is we're going to graph y equals negative x minus 1. So let's see, that's a line with y-intercept negative 1 and slope negative 1. So it's going downhill. It's going downhill with a slope of negative 1. And it just occurs to me that because when I before said slope negative 1, I was also writing this x-coordinate negative 1. That might have been confusing. Having a slope of negative 1 means it's going to go down 1 for every one it goes across. So for example, I know that when x is 1, the y-coordinate's going to be negative 2 because it's going to go down 1 for every one it goes across. So I was just working backwards, and I knew that it must then go through negative 1 on the x-axis. But that negative 1 on the x-axis and on the y-axis, they have nothing to do with the slope being negative 1. It's just kind of a coincidence that there's so many negative 1s in this inequality. Anyway, so I've graphed this line, and the reason it's dotted is that I don't have greater than or equal to, just greater than. And a dotted line is how we show that there's a boundary, but the boundary's not included in what we're graphing. Now, this inequality is saying we want all the y's that are greater than the y values that are on the line y equals x minus 1. So this is the line y equals negative x minus 1. And where are the y values greater than these y values? Well, they're above, because y values get bigger as you go up. So when you're graphing a linear inequality like this, you're going to be shading in half the xy plane, and the boundary line between the stuff you shade and the stuff you don't is the line that you get by replacing the greater than with an equals. Now, what about this business of x not being equal to y? Well, that then means we can't have any values on the line where x is equal to y. In other words, we can't have anything on the line y equals x. So I'm going to put a dotted line there indicating, okay, our domain is all of the pink stuff, but not the stuff on the dotted line.